Greetings everyone, welcome to Side A, Side B. In this video, a discussion on how the periodic functions are derived from the unit circle. The overall plan discussed two items. First, putting the x-axis in terms of circumference, and then checking on a graph. So what's in our toolbox? How about what we know from previous studies and a circle? Let's dive in. In our last video, we plotted the entire unit circle on a graph. We plotted the orange arrows on the graph, the result of varying the orange triangle using two intervals of x. If we combine the intervals, we get the following restricted domain in the white box. X is greater than or equal to -1 and less than or equal to 1. Upon moving in the direction of the white arrow of the domain, the entire unit circle is plotted, which includes the lavender arrows. See that? Let's put everything into perspective, because we really plotted the formula in the blue box, along with its reflection, using a restricted domain, and the x values are cosine, the y values are sine. If we rotate the circle, it shows what's really happening. The x-axis on the unit circle corresponds with the graph. Both are the vertical now. For example, the red arrow on the unit circle matches with the red arrow on the graph. The pair is x equals 1, y equals 0. So the blue lines have the value 0. Then we varied x in the direction of the white arrow. Now observe orange arrow 1 corresponds to orange 1 on the graph. The same can be said about orange arrow 2, along with their reflections in lavender. So we can safely say when x equals 1 or -1, y equals 0, the blue lines, and when x equals 0, y equals 1 or -1. See that? Why lavender? We wanted to use purple, but purple doesn't show up as well on the blackboard. So lavender is really just a muted down color of purple. Oh! Well, the graph might seem confusing at first, because that's not the way we usually see one. But as it turned out, this is the graph we get when we plot the blue box. Nice. Because we have a function, and its graph, just its domain is restricted. I know. What we really want though, a graph of y equals cos x, where x is not restricted, and it plots cosine as a type of wave function, preferably more friendly than what we have. So how can we do that? Humans realized they could use what they knew about a circle to help solve that problem by putting the x-axis in terms of the circumference of a circle, and then the range became y is greater than or equal to -1 and less than or equal to 1. Next blackboard, please. Ladies and gentlemen, are you excited as much as we are? Because we're about to do a mind jump, and everyone is invited. We have to make an assumption. Until we prove the value of pi, for now, we're assuming its value and how it's derived, which is the ratio of the circumference of a circle over its diameter. In order to prove it, we need to use the concept of a limit. If so, then let's continue. So, if we have c equals circumference equals 2 pi r, then by the Pythagorean identity, we let radius r equal 1. It's not reflected on our unit circle. We put the x-axis in terms of c. Then the previous domain of x becomes, for now, x is greater than or equal to 0 and less than or equal to 2 pi. And the range of y was mentioned already, which means we have to rotate our unit circle back to its original position, but for a bigger and better cause. Let's see how we can put the x-axis in terms of c. Observe, if we begin at the point 1, 0, going counterclockwise, orange arrow 1 goes from 0 to pi, which is point -1, 0. It follows orange arrow 2 goes from pi back to our original point, or 2 pi. Does that make sense? At this point, our intuition should be popping. At the point cos 0 and cos 2 pi, our y should equal 1, which corresponds to the cosine value of 1. The next point we should match up the point that lies in between 0 and pi, which is straightforward enough. It's half of pi, or pi over 2, the top blue arrow. The other midway point is the bottom blue arrow. Doing another mind jump, what's pi plus pi over 2? We have 2 pi plus pi all over 2, which just equals 3 pi over 2. Those are the points when y equals 0. Our intuition should be popping again. Observe, we have different x values that translate the reflection such that instead of one x value for the same value, now we have two different x values for the same value. Recall the x of the 4 points on the unit circle are cosine values. We want to keep them, correct? However, in order to plot them, we have to use a different method. So just consider for a moment what we're about to do. If those x values can stay where they are, all we need to understand, the circumference of a circle will naturally match up with those values. Okay, if your intuition said, if a cosine wave begins at the point 0 and 1, we must have cos x equals 0 and y equals 1. The 1 in the yellow circle corresponds with the x value of our original pair, but now the y value is crossed out because we no longer need it. We didn't mean it that way. We don't need it to plot cosine, but we need it to plot sine. Then on to the next point. We can do the same. If we have x equals pi over 2, then y equals the orange 0. The y is crossed out from the original pair. Do the same for the remaining points until we get to x equals 2 pi, then orange y equals 1. But this time, we have two different x's which equals the same value 1. Now makes a type of wave function. That's what we want. Very nice. Our next blackboard is repeating and refining what we just said. Notice the point cos 0 and 1 coincides with the point in the orange circle on the graph, upper right. And then observe the orange arrow values are related. All the white dots on the x-axis correspond with their appropriate y values. For example, the point cos pi and -1 corresponds with the yellow arrow. The point cos 2 pi and 1 corresponds with the red arrow. Voila! We plotted cos x equals y, using our new domain in the white box, the x-axis in terms of c. If you don't know already, the coordinate system is divided into 4 quadrants, in the blue circles read counterclockwise. Recall the red dots, but this time the x value for the red dot in the first quadrant. Doing some mental math, what's half of a half? A quarter. So naturally, the x value is pi over 4. Its y value, recall the original pair of the red dot, x equals square root 2 over 2, and its duplicate, y value. Then, the original x value is the new y, which coincides with 45 degrees. Is that really the case? We'll check it out very shortly. In quadrant 2, we have 3 pi over 4. In 3, 5 pi over 4. Lastly, in Q4, 7 pi over 4. Because of reflection, the y value in quadrant 1 will be the same in quadrant 4. The same can be said for Q2 and 3. As a heads up for what's coming next, the value of square root 2 over 2 in the neighborhood of 0.70711 rounded off. Alright, Now for something very appropriate to the discussion, some moving frames, as it were, checking the work. Let's begin. Welcome back. Hopefully the mind jump wasn't too bad, ladies and gentlemen. We just found this site. We have the graph of y equals cos x. What are the 5 points of our wave? Let's check the values. Cos 0 and 1, that's what we want. Good start. Notice the x-axis is in terms of c, the circumference of a circle. Then we have pi over 2 and 0. Our next point is pi and -1. And then 3 pi over 2 and 0. Lastly, the point x equals 2 pi and y equals 1. Matches with all 5 points. So far, so good. We think seeing it on the graph helps the integrity of the discussion. What do you think? It looks like we're on the right track, but let's check the 4 other points. The first quadrant, pi over 4, blue line. That's the value we want on the x-axis. There's our pair. X equals pi over 4, y equals square root 2 over 2, rounded off. 0.70711. Then we check its counterpart in quadrant 4. X equals 7 pi over 4, the black line. The value checks out on the x-axis. Then its point on the wave function. The y value matches with what we expected. Nice. Moving right along, folks. The value in quadrant 2, 3 pi over 4, the green line. The value checks with the x-axis. On the wave, the y value also checks out. Negative square root 2 over 2. Now its counterpart in quadrant 3, 5 pi over 4, the purple line. We somehow got the purple worked in there. And the value checks on the x-axis. Nice. Lastly, the y value checks out on the wave function. See that? Xing out. Now, let's check the function. Check some random values. What if we have x equals 3 pi? What can we predict? If 2 pi is 1 period, then if we sum with pi, we should get -1, because 3 pi is half the next period. Three pi is where it should be on the x-axis. On the wave, y equals -1 also checks out. Let's do one more. Since 1 period equals 2 pi, the next period is, drum roll please, 4 pi. Checks out on the x-axis. Also the point on the wave function. One more. Half of the next period will be 5 pi. Checks out on the x-axis and the wave function. 3 periods equals 6 pi checks out on both points. And so on and so on. If the x-axis is in terms of c, or more formally, the axis, is labeled in radians, let's pick a random value of, say, 30. How will it be plotted? Just consider the value 9 pi, which is equivalent to 28, but less than 30. Then consider 10 pi, which is equivalent to 31, but greater than 30. Then 30 should be somewhere in between. Let's plot it on the green line. There it is on the x-axis, and the pair on the wave function. So that's how 30 gets converted in terms of c, or radians. What's the period? 5 times 2 pi equals 10 pi, so 30 is plotted in the 5th period. Observe its y value because we'll refer back to it. To conclude our discussion, let's see how a graphing calculator interprets radians. Let's just check 4 values. This is not a sponsor or anything like that. We just found this site. To start, make sure the calculator is in radian mode. From quadrant 1, cos pi over 4 returns what we would expect, the positive decimal value of square root 2 over 2. Then its reflected value, in Q4, cos 7 pi over 4 returns the same value as expected. The next pair of interest, in the second quadrant, cos 3 pi over 4 returns the negative of square root 2 over 2. One more pair to check. In Q3, cos 5 pi over 4 returns the reflected value. Everything checks, which is nice. Checking beyond the first period, cos 3 pi returns negative 1. Two periods is what? 4 pi returns 1. Recall the y value of our random number 30. That checks with the calculator. Let's check, since we're here, in degree mode. We haven't discussed this yet, but cos 30 in degree mode, the calculator will interpret 30 in terms of degrees. So y will be the exact value square root 3 over 2, or its following decimal value. Just briefly, the inverse of cosine is arc cosine. If we're in degree mode, we just saw cos 30 equals its corresponding y value, square root 3 over 2. Then, the inverse of cosine, arc cosine, of square root 3 over 2 equals 30 degrees. We're really just applying algebra, as if we're dividing each side by cosine. See how that works? A discussion of arc cosine and arc sine is on the books. Like we said before, doing discussions like this helps our channel, helps our own understanding. If you also get something from these discussions, would be a bonus, and make our day. If your calculator is in degree mode, cos 30 will return that value. If your calculator is in radians, will return another value. Well, what about the sine function? The same reason we didn't do the study on the sine wave, we can just replicate the study that we just did for sine. And that concludes that. So that can save some work. But we're not quite finished. What happens if we put in negative values for x? Like negative pi returns negative 1. Then negative 2 pi returns 1. The calculator interprets the negative and positive values as if they were the same. Believe it or not, there's a good reason for that. Finally, did you guess the theme of today's discussion? Mind jump. We started with the domain of x as 0 through 2 pi, but finish off, if humans were not convinced of the idea of infinity, then they should have been when they realized the domain of the cosine function can be represented as negative infinity through positive infinity. When we put in negative or positive values, the reason why the cosine function interprets them as if they were the same. The reason is a visual, because cosine is known as an even function, and we refer to it as being symmetric about the y-axis. Which means, if you fold the graph along the y-axis, the two halves match up. Notice, if you rotate the graph 180 degrees, is going to pivot on the number 1. We'll end up with a totally different graph. Whereas an odd function, like sine, is symmetrical about the origin, meaning if you rotate the graph 180 degrees around the origin, it remains unchanged. But if you fold the graph about the y-axis, the two halves do not match up. So we still need sine, as odd as it is. Yet, infinity, as boundless as it is, at the same time, a strange idea, because there's really no way to mathematically check infinity, unless we also consider using limits. On that note, we need to consider using the restricted domain so we can end the video here. Until next one, ladies and gentlemen. And if we're going to end it, we just end it right there.